Hey guys, this is Mrs. Hardman, and we are going to take a look at 6.3, Zeros and Inequalities of Quadratic Functions. Let me go ahead and select my pen color here, and let's get started. Our biblical integration for today is that God provided 4 different gospel accounts in His holy word that provide us different insights into the same story. We have Matthew, Mark, Luke, and John, all giving us the story of Christ, but from different perspectives because they were written to different audiences. Graphing equations helps us to see written information from a different perspective. Some people may prefer charts, some people may prefer a written report, and others are going to prefer graphing. So graphing is a really visual way and another way to show the same information from a different perspective. Our lesson objective for today is that you, the student, will determine the real zeros and y-intercepts of a quadratic function, and will solve quadratic equations and inequalities with 2 variables. Let's get started by reviewing how to find the vertex of each function. If you look at y equals 2x squared plus 7, hopefully you notice there's no linear term, there's no x term. And you remember that in that case, the vertex is just 0 plus the constant term. So our vertex is 0, 7. In our second example, it's written in vertex form. And hopefully you notice that our vertex is 4, 11. Now the last one is also written in vertex form, but there's no constant out here. That means that our vertex is -2, 0. Remember, vertex form is x minus h, with h being the x value there, the horizontal value. If you have x plus 2, what you really have is x minus -2. So our x value is -2. Don't forget about that. Let's also go ahead and practice stating the domain and range of a function. We have y equals 5 times x plus 1 squared plus 3. Now you've heard me say before, and hopefully you haven't forgotten, that the domain of a quadratic function, which is what this is, we've got a squared term here, is always all real numbers. And the range is based on the vertex. And now this parabola has a positive number, so that tells us that our parabola is opening upward. And so our vertex is going to be a minimum point, which means everything is going to be greater than our lowest y value. Well, our vertex is -1, 3, so our range is that y must be greater than or equal to 3. It must be greater than or equal to this y value out here. Let's go ahead and write this in vertex form. Just as a quick little practice here, the first thing we're going to do is bump out the -1 so that we have just the quadratic and the linear term in parentheses. Then we'll go ahead and factor out the 2. Once we factored out the 2, we can complete the square by taking half of our b term, this is our b term, and squaring it. So 3 over 2, that's half of our b term, squared, is 9/4. Now we didn't just add 9/4 to our equation, we added 9/4 times 2, or 18/4. If we have an 18/4 that we've added, we need to put a -18/4 on the outside here to balance it out. Let's go ahead and simplify that 1 by making it -4/4, and go ahead and factor using our little shortcut here for a perfect square trinomial. We take the square of the first, the sine of the second, and the square of the third. So we get 2 times x plus 3/2. The whole thing is squared. And then -4/4 and -18/4 becomes -22/4, which simplifies to the y-intercept of the quadratic function f of x equals ax squared plus bx plus c is 0, c. So our y-intercept is our constant term. And you can see that is crossing the y-axis right there. That's our y-intercept. So if we were to make all of our x's 0, which is what's true when we have a y-intercept, then we can see that's why it's the constant term. In order to find our x-intercept, our y has to be 0. So the y-intercept of the quadratic function is 0c when x is 0, but the x-intercepts can be found by setting the whole equation equal to 0, or making our f of x equal to 0, and then solving for x. Now the way that we solve for x is by factoring, by taking roots, or by using the quadratic formula. A 0, or root of a function, is a value of x for which f of x equals 0. Remember that f of x is just another notation for y. So a 0, or root of a function, is a value of x for when y is equal to 0. And we know that's the case. We know where it crosses the x-axis, y is equal to 0, or f of x is equal to 0. A function's real number zeros are the x-coordinates of its graph's x-intercepts. And we Talked about that a lot, that a 0 is the same as a root, is the same as an x-intercept. Let's find the y-intercept and the zeros of this function. R of x equals 1/2 x squared plus 2x plus 2. Now, in order to find the y-intercept, we just make our x's zeros. We can do the math there, or we just know, because those are zeros, our y-intercept is our constant term. So our y-intercept is just 2, or 0, 2. To find our x-intercepts, or our zeros, or our roots of this function, we need to say that r of x is equal to 0. So we get 1/2 x squared plus 2x plus 2 equals 0. We can multiply this whole thing by 2 to get rid of that fraction. And now we have x squared plus 4x plus 4. By factoring, we factor that into x plus 2 times x plus 2. Then we use the zero product property to set each of our factors equal to 0. So x plus 2 equals 0, or x plus 2 equals 0. In either case, x equals -2, or x equals -2. So we have 1, 0, x equals -2 with a multiplicity of 2. It appears twice, here and here. Let's go ahead and find the y-intercept and zeros of this function. S of x equals -2 times x minus 1 squared plus 8. Just like before, our y-intercept here, we're going to plug in 0. Now this time, we can't just take the constant term because it wasn't in standard form. This time we do have to plug in our 0, and we do have to do the math. And when we multiply all that out and simplify, we find out that our y-intercept is actually 606. To find our zeros, we're going to take s of x and set that equal to 0. So we get -2 times x minus 1 squared plus 8 equals 0. We're going to subtract 8 from both sides, and then we still need to get the x minus 1 squared term by itself, so let's divide by -2. And we get x minus 1 squared equals 4. We undo squares by taking the square roots, so we're going to take the square root of both sides, and we get x minus 1 equals plus or minus 2. We'll then create two different equations, x minus 1 equals positive 2, and x minus 1 equals -2, and solve for x. When we do that, we find that x is equal to 3, or -1. So our zeros are x equals -1 and 3. Let's find the zeros of p of x equals -x plus 2 squared plus 6. Because we're finding the x-intercepts, we need to set our y, or our p of x, equal to 0. And we get -x plus 2 squared plus 6 equals 0. We'll subtract 6 from both sides to get the x term isolated here. We'll then divide by -1 to get rid of this negative here, and we get x plus 2 squared equals 6. We undo a square by taking the square root, so we get x plus 2 equals plus or minus square root of 6, since 6 is not a perfect square. We then need to subtract 2, and when we do that, we get x equals -2 plus or minus the square root of 6. If we were to type this into our calculator to get decimal estimates, we get x is approximately 0.45 and -4.45. All right, go ahead and find the zeros of q of x equals x squared minus 2x plus 3. We set that equal to 0, and when we try to factor it, we find out, unfortunately, it's not factorable. So we do need to solve this by using the quadratic formula. Let's go ahead and identify our a as 1, our b is -2, and our c is 3, and plug that into our formula. -b plus or minus the square root of b squared minus 4ac all over 2a. From there, we simplify algebraically, and we get 2 plus or minus the square root of -8 all over 2. But we're not quite done simplifying that. We can simplify that even further to become 1 plus or minus I root 2. Now, I'm going to show you how we simplified that in case we lost you here. Because we have two terms and a common denominator, we can write this as 2 over 2 plus or minus the square root of -8 over 2. Well, 2 over 2 just simplifies to 1, so that's where the 1 came from. Square root of 8 over 2 is the same thing as 4 times 2 times negative 1. Square root of all of that over 2. Well, I can take the square root of 4. That comes out. And I can take the square root of negative 1. That's I. I can't take the square root of 2, so that stays under. And all of that is over 2. We then can simplify 2 over 2. Those cancel, which leaves us with I root 2. So that's where the second piece came from. And that's how we ended up with 1 plus or minus I root 2. A quadratic function has either 2 real roots, a double real root, or 2 complex roots. It is quadratic. There is an x squared term, so you are going to have 2 of some kind of root. The solution to a single variable quadratic equation or inequality can be found graphically by finding the zeros of its related quadratic function. Graphing quadratic inequalities is similar to graphing linear inequalities. First, we're going to graph the related function, so we're going to graph it as if it were an equal sign. Then we'll use either a solid or a dashed curve. We'll use solid if it's greater than and equal to, less than or equal to, and we'll use dashed if it's just greater than or less than. And then we'll shade the appropriate region, above the curve or below the curve. Above the curve if it's greater, and below the curve if it's less. Let's try one together. We're going to graph y is less than negative x squared plus 4x minus 3. The first thing that we want to do is graph the related function. We're going to identify our y-intercept when x is 0, and we find out that it is 0, 3. We're also going to find our zeros. When y is 0, we get that it is factorable, so x minus 3 and x minus 1 are the two factors, so our two zeros are 3 and 1. Our vertex can be found by completing the square. When we complete the square, we find out that our vertex is 2 and 1. And now we have enough information to graph some points. So we'll graph our y-intercept in green, our zeros in red, and our vertex in purple. Now, if this were an equal sign, we would just connect our points and make a nice parabolic curve. This is, though, an inequality, so we need to look at the sign, and it does say less than, not equal to, so we need to draw our curve with a dashed line. Then, because it is less than, not greater than, we need to shade below the curve. You can see that shaded in blue on our picture. Easy peasy. Just like graphing a parabola, you just change the dotted line, change to the dotted line, and shade the appropriate region. Today we determined the real zeros and y-intercepts of a quadratic function, and we solved quadratic equations and inequalities with 2 variables. If you guys have any questions, be sure to write those down and ask me next class.